The mystery of Betelgeuse, a colossal presence in the constellation Orion, continues to fascinate both professional astronomers and casual observers of the night sky. To the naked eye, it appears as a steady reddish star marking Orion's shoulder, quietly glowing within one of the most recognizable patterns in the sky. Yet that calm appearance is profoundly misleading. What looks like a stable point of light is in reality one of the most unstable and dynamic stellar systems visible from Earth. Compared to our Sun, the difference is not only one of size, but of evolutionary stage, internal physics, and ultimate destiny. The Sun is a stable, middle-aged main sequence star maintaining a delicate balance between gravity and nuclear fusion. Betelgeuse, by contrast, is a red supergiant approaching the final stages of stellar life, a star that has exhausted much of its core hydrogen and expanded into an enormous, turbulent envelope of gas. Its deep reddish color is the first visible clue to this transformation. Unlike the Sun's white-yellow light, which reflects a stable surface temperature and balanced fusion process, Betelgeuse emits a subdued red glow that signals cooling outer layers and an enormously expanded atmosphere. This change is not cosmetic. It reflects a profound internal restructuring. As hydrogen fuel in the core becomes depleted, the star reorganizes itself into layered shells of fusion. Hydrogen continues burning in outer regions while helium and progressively heavier elements fuse deeper inside. This layered structure is often described as onion-like, with each shell representing a different stage of nuclear processing. But unlike the stable core of a smaller star, these layers are far from steady. They are unstable, constantly shifting under the influence of violent convection currents that reshape the star from within and drive it far from equilibrium. These internal instabilities manifest dramatically on the surface. Betelgeuse is not smooth or uniform. Its surface is dominated by enormous convective cells, vast regions of rising and falling plasma that can span a significant fraction of the star itself. If observed up close, its surface would not resemble a calm glowing sphere, but a boiling, chaotic ocean of gas where gigantic bubbles of superheated material rise, collapse, and reform continuously. These convective motions are so large that they directly influence the star's brightness. As hotter material rises toward the surface, Betelgeuse brightens. As cooler regions dominate, it dims. This is one reason its light output fluctuates over cycles ranging from subtle variations to dramatic changes visible even from Earth. One of the most widely discussed episodes in recent astronomy was the so-called Great Dimming event between 2019 and 2020. During this period, Betelgeuse noticeably decreased in brightness, triggering widespread speculation that it might be approaching a supernova explosion. While dramatic theories circulated in public discussion, scientific analysis pointed toward a more grounded explanation. A large cloud of dust, likely ejected from the star itself, temporarily obscured part of its light. This dust formed from cooling stellar material expelled into space, acting like a transient veil that reduced the star's apparent brightness. Yet the event still revealed something crucial. Betelgeuse is actively shedding mass into its surroundings, a clear signature of late-stage stellar evolution rather than stability or calmness. The scale of Betelgeuse is difficult to comprehend in human terms. Located roughly 640 light-years from Earth, the light we see today began its journey long before modern civilization existed. Even at light speed, we are observing the star as it was in the distant past. And yet, despite this vast separation, astronomers can reconstruct detailed information about its structure, temperature, and internal behavior. Modern telescopes, including space-based observatories and high-resolution interferometric systems, allow scientists to map surface activity and infer internal dynamics with surprising precision. Betelgeuse is no longer just a point of light. It is a partially resolved physical system undergoing measurable and ongoing change across both time and scale. If placed at the center of our solar system, Betelgeuse would extend far beyond the orbit of Mars and potentially approach the region of Jupiter. In such a scenario, Earth would exist deep within the star's outer atmosphere, immersed in hot, diffuse stellar plasma with no clear boundary between planetary space and stellar envelope. The entire inner solar system would effectively become part of the star itself. This comparison highlights not only its immense scale but also the fragile position of planetary systems within the broader cosmic hierarchy, where stars are not gentle lights but evolving, consuming, and reshaping forces of nature. Beyond its size, Betelgeuse is losing mass at an extraordinary rate. Powerful stellar winds continuously eject material into surrounding space, forming arcs, shells, and irregular clouds of gas and dust. These outflows enrich the interstellar medium with heavy elements, contributing directly to the chemical evolution of the galaxy. In a profound sense, Betelgeuse is not only a dying star but also a source of creation. The material it releases will eventually become part of future stars, planets, and potentially the chemical foundations of life elsewhere in the universe. Stellar death, in this context, is not an ending but a redistribution of cosmic matter into new structures yet to form. Inside the star, nuclear fusion continues in increasingly unstable layers. As lighter elements fuse into heavier ones, the core gradually builds toward iron. This stage is critical because iron cannot release energy through fusion. Once iron accumulates, the star loses its ability to sustain outward pressure against gravity. At that point, equilibrium collapses, leading to core collapse and a supernova explosion, one of the most energetic events in the universe. If Betelgeuse were to explode, it would become temporarily visible in daylight on Earth. While it would pose no physical threat due to its distance, it would transform the night sky into an extraordinary astronomical event lasting weeks or even months, permanently altering Orion's familiar appearance. However, the timing remains deeply uncertain. It could occur tomorrow in cosmic terms, or it could take tens of thousands of years. There is also a more intriguing possibility. The explosion may have already occurred, and we are simply waiting for its light to arrive. Because light travels at a finite speed, the star we observe is always a delayed version of reality. What we see is not Betelgeuse as it is now, but as it was centuries ago. This delay transforms astronomy into a form of time observation, where distance becomes history and every image becomes a reconstructed past rather than a present moment. Despite its instability, Betelgeuse is not merely a symbol of destruction. It is also a mechanism of cosmic renewal. When it eventually explodes, it will scatter newly formed elements such as carbon, oxygen, silicon, and iron into space. These materials will mix with interstellar clouds and eventually form new stars, planets, and potentially environments suitable for life. Without such stellar deaths, the universe would lack the heavy elements required for rocky worlds and biological chemistry. In this sense, Betelgeuse is part of a continuous cycle where destruction enables creation, and endings become the raw material for beginnings. Modern observations have also revealed subtle oscillations within the star, often described as stellar pulsations or starquakes. These vibrations allow scientists to probe its internal structure in a way similar to how seismic waves reveal Earth's interior. By analyzing these oscillations, astronomers can infer density variations, temperature gradients, and internal layering. This technique has transformed Betelgeuse from a distant point of light into a partially understood physical system with measurable internal dynamics, bridging the gap between observation and internal structure in stellar physics. Ancient civilizations observed Betelgeuse without knowledge of its true nature. Yet even then, its brightness variations and reddish hue were recorded in early astronomical traditions. Today, with advanced observational tools, those same variations are understood as signatures of complex physical processes unfolding on a massive scale. What once appeared fixed in the sky is now recognized as a star in transition, actively reshaping itself as it approaches the final stages of stellar evolution. Ultimately, Betelgeuse represents a critical phase in the life cycle of massive stars, one that is both dramatic and essential. It reminds us that stars are not eternal fixtures, but temporary structures governed by internal physics and cosmic time. Its instability, variability, and eventual fate are all part of a larger galactic process that recycles matter across the universe. Every element within Earth, including those essential for life, was once forged in stars like this. As Betelgeuse continues its slow transformation, it stands as a visible reminder of the universe's ongoing cycle. Stars are born, they evolve, and they die, but in doing so, they seed the next generation of cosmic structure. Even in its final stages, Betelgeuse is not an ending. It is a transition point in a much larger story where energy, matter, and time are continuously reshaped across the fabric of the universe, quietly preparing the conditions for whatever comes next in the long unfolding history of the cosmos.